Wanted to start by thanking everyone so much for joining us today. This is a bit earlier than our usual webinar time, so appreciate your flexibility and attention to detail there. I'm going to get started with a quick land acknowledgement. So this webinar takes place on Ndakina, which translates to our homelands that is now called New Hampshire and Vermont. Ndakina is the unceded traditional ancestral homelands and waterways of the Pennacook, Abenaki, and Wabanaki peoples, past and present. We acknowledge and honor with gratitude the land, water, air, flora, and fauna, and the human beings who have stewarded Ndakina throughout the generations for over 12,000 years. I also want to give a thank you to the Nature Conservancy and the Colony Group, our corporate sponsors, for allowing this webinar series to keep running. And then getting into the meat of the presentation today, I'd like to introduce Paul Bemis. He is the president of Granite State ASHRAE. He is an expert in building science and has been working in the fields of energy efficiency in the built segment for over 30 years. He is a mechanical engineer from UNH. He's an electrical engineer, and he currently owns a software and consulting company in New Hampshire that is a top supplier of thermal modeling software and services for the mission critical data center market. So today we're lucky to have him joining us for what we learned from COVID-19 about the indoor air environment and how to use that knowledge to prepare for the future. So Paul, thank you so much again for being here and for letting us record this presentation for everyone else in our group. And I will pass it over to you. I invite folks to put questions in the chat throughout, and we'll have some time to answer those after the talk. So Paul, over to you.
Okay, I think you need to let me share.
All right, try that.
Yep, there we go. Thank you. All right, thanks everyone for joining us today. I'm going to be talking about what we've learned since COVID-19, specific to the healthcare industry, but it's kind of a general presentation talking about mitigating the transmission of airborne pathogens. And it's general to not only healthcare, but it's general to indoor spaces in general. As Emily told you, my background is both mechanical and electrical. I really grew up doing mechanical engineering, electronics packaging, with a heavy emphasis on thermal environments, which are air, airflow. And so that got me interested in computational fluid mechanics. I also became quite heavily involved in computer design, working for Hewlett-Packard, and then fluid mechanics and structural mechanics with ANSYS and Fluent. So I have an unusual background in that I have both mechanical and electrical background, and also business, of course. I own two companies at the moment. One of them is Applied Math. As Emily mentioned, we do thermal modeling and design optimization for data center design. I also have another company I started during COVID-19 called Air Cleaners, and that has more to do with air quality inside environments, such as the one you're sitting in now. So I will use that platform mostly for our discussion today. So we're really here talking about SARS-CoV-2, but I want you to understand that SARS-CoV-2 is really the straw that broke the camel's back in terms of airborne pathogens. We are now finding that most things are passed through airborne transmission, including SARS and MERS and common influenza, the cold, tuberculosis, measles, common flu, annual flu. All of these things are airborne. In fact, it appears now that the airborne transmission path is the most highly likely path of transmission for all of these things, and possibly more. And that COVID-19 won't be the last pandemic we face in this area. So it's important to understand what is a proper indoor air environment and how to get there, and where you might be now in terms of indoor air quality. So it's really quite important. By the way, the idea of humans being in an indoor environment is relatively new in terms of our evolution as a species. Human beings spent the first several million years outdoors, and it's only since the industrial evolution that we've gone indoors. And the indoor environment is not well suited for us as humans. So we are indoors. We spend more than 90% of our time indoors now as humans. And so the indoor air environment is going to continue to become more and more important. So we're going to be talking about SARS-CoV-2 here primarily, but all their variants, including mold spores, allergens, and dust. So the history dates back to the 1930s on this. A fellow named William Wells worked on tuberculosis transmission, and they thought at first that there was this cutoff level at 5 to 10 microns of size, and that it would fall off quickly after that in terms of size. What we find is that that's not the case, that these coughs and sneezes and talking loudly are really multi-phase events, multi-phase turbulent, which means they have liquid and solid and gas in their output. It's moist, warm air that comes out of your face and nose and so forth, and that it can extend to distances up to 100 feet per second and 30 feet away from where you are. It is heavily influenced by indoor air temperature, humidity, and airflow. And once evaporated, they can stay in the air for hours. The half-life of the CoV-2 pathogen is 1.1 hours. It is also true for influenza, it's 1.1 hours. So these things have a lot in common, and they tend to float, particularly the small ones. They float on the air. They float on the thermal currents in a room. Now, there's different transmission routes. There's direct contact. That's, shaking hands with someone. There's indirect contact, where you touch a doorknob or a handle that someone else has touched. There's large droplet spray, which some of you unfortunately have felt when someone's too close to you or sneezes or is talking to you loudly in a confined environment, and you can feel it. Not a pleasant thing. And then there's aerosol. Today we're going to be talking about aerosol, and it has traditionally been defined, as I said, by Wells back to the 1930s as having a specific size. But that's not really true. We've learned a lot. We learned a lot through both experimentation and analysis of situations, and also computational fluid modeling, which is one of the areas that I specialize in. So airborne transmission became important early on in the COVID pandemic because we saw these things happening. Like, if any of you remember, it seems like a long time ago, it wasn't that long ago, that we had the Skagit choir, a valley choir, where 53 of 61 members tested positive after a choir practice, after a 2.5-hour practice. We had the Diamond Princess cruise, where, a good third of the people became sick. We had the bus trip, where on one side of the bus, people got sick. On the other side of the bus, they didn't. We had the restaurant, where 10 out of 68 people became infected in the same area of the restaurant. And then we had the call center. So these are all what we call super spreader events, and they were places that we had the opportunity as scientists to study just exactly what the situation was, some more than others, but clearly these stood out as events. By the way, no transmission outdoors. So there is no transmission of these airborne events outside. It's only in the building. And so air quality inside of buildings is becoming more and more important for these reasons. The transmission mechanics are really that there's this thing called a viral load. And the viral load, let's see if I can, yes, I think I can. Yep. So the viral load comes from this spray that comes out. The viral load is defined by the amount of virus per unit volume. Some tend to spread more heavily than others, some people, because they're at a different point in their incubation life of the pathogen. And so the viral load can be higher because there's more virus per unit volume. And what happens after someone breathes or sneezes or sings, depending what they're doing, is it becomes very, very light. It dries out, particularly if the humidity is low. And one of the things that's characterized by New England winters in particular is low humidity. Low humidity tends to dry out the droplets. And when they dry out, they become light and they float on the air current in the room. The air current primarily driven by either the cooling system or heating system, or just the temperature in the room, the thermal temperature of the room. By the way, each one of us is about 100 watts of energy that we put out. So you can think of each one of us as a light bulb. And if you've ever gotten close to a light bulb, you know it gets pretty warm. We're 98.6, and we create a thermal plume ourselves that goes up. And in an environment where the ceiling is low, it hits the ceiling and begins to spread and fills the room with a concentration. And then it transmits. Now, what we also have learned through the science is that the infection period is really a little after 3 days, about 3 days, it starts to peak. So it peaks right in this region of about, this is sort of the infection here, where you sort of get the infection, and over here you see the symptom. This is the problem, is that it's peaking before the symptom is seen. This is why things like temperature testing and even COVID tests don't necessarily help you much, because you're not symptomatic until you're really over near this curve. And this is why, testing is not perfect, because you're quite susceptible. Probability of transmission is highest prior to symptom. So that's why, and then it drops off. Once you see the symptoms, it drops off. 2 days later, 4 days later, it's dropping quickly. So, and difficulty breathing is over here at 6 days. You can see why transmission happened a whole lot during this period, because no one even knew they had it. No one even knew they were transmitting it. Yet they were transmitting it more during that period. The viral load was heavier early on before symptoms even occurred. Still true today. It's also true about the common cold. By the way, COVID-19 is here kind of a proxy for the common cold or for the viral flu, the annual flu. All these things behave the same way. Size of the droplet is important. As the droplet gets smaller, as it becomes smaller, it gets lighter. Now, we say here that the virus is not naked. It tends to hang around. It attracts itself. So the actual virus itself is about 0.1 microns. But it generally hangs around respiratory fluid. It attaches itself to liquid, and as the liquid evaporates, it becomes lighter. And this does determine how long it stays in the air, how far it can travel, how quick it falls to the surface, where it deposits, and the respiratory system is a function of this as well. Our respiratory systems are best when there's humidity in the air, because the upper respiratory section of our bodies is a major preventative of airborne pathogen, but it needs liquid to behave itself really well. The cilia in our upper respiratory tract is a disease prevention mechanism, and when it dries out, it's less effective. And then the pathogens, the particles go deep into your lungs and tend to infect you quicker and more seriously. So masks help and filters help. We'll talk more about masks and filters, but the physics is all the same. You want these things to not be there in the first place, or if they're there, you'd like to keep them as large as possible with water, so it falls to the ground. And you'd like to have water in the air so that our defense mechanisms work better. This doesn't lend itself well to New England, by the way. New England is characterized by, in the wintertime, cold and dry. The dryness makes our respiratory systems less resilient and more susceptible. And the dryness also tends to make the pathogens last longer in the air. They hang longer. As I mentioned, their half-life is over an hour. So this is just a plot that shows you that as humidity goes down, the evaporation with it goes up. So what you want is it evaporates, the particles get smaller. So you can see they drop very quickly from right around 10 microns down based on relative humidity. Across my horizontal axis is humidity, so I'm down here at 20%. I'm up here at 100%. Now, you generally want your humidity to be between 40 and 60%. You want it in this range, both in your homes and in your lives. Humans are much happier when their relative humidity is in this range. But if it drops below 40%, these particles get really small and they hang in the air for a much longer period of time. In terms of size, I've given you here a bit of a chart that shows you the different sizes. PM2.5 is the particle. That's what we're talking about, is particles in this range of PM2.5. There's an example of it compared to a human hair right over there. So here's beach sand. Here's a human hair. This is just a graphical representation. Human hair is about 50 to 70 microns apart. The PM10, which is a particle count that we look at, 10 microns, is about this size. PM2.5 is awfully small, and that's a 2.5 micron particle, and we're finding that we're down below, down in the range of 1 micron when these things dry out. The pathogen itself is 0.1 micron. So these are very, very small. They obviously can't be seen. This is one of the other problems, and they float. So this is just a representation, kind of a cartoon representation of the ways to improve the situation. One of them is ventilation. We're going to talk about this a lot. So the change in concentration with respect to time can be affected by settling. This is gravity. This is our old friend Isaac Newton that just pulls it to the ground. Ventilation and air exchange. This is very important, and we're going to be talking more about ventilation in a moment. Inactivation. You can kill it with things like ultraviolet light, for example, kills it. So UV light is a way to do it. And C sub D, of course, is the concentration itself. So you can let it fall by itself over time. You can try to ventilate it or clean it with a filtration system. That's become probably the most effective. You can inactivate it. That's an engineering kind of approach with a special kind of light. Spectrum of light has to be a certain wavelength to kill it. So here's a plot of, again, the size. This is half-life. So the half-life of the particles for CoV-2 and CoV-1 both are in that range of 1.1 hours at a relative humidity of 65%. And it survives about 16 hours at 53%. So it hangs around a long time. Again, the half-life is about 1.1 hours. So it hangs around. And this is why we have witnessed events where people come into an environment that has no one in it and they get COVID in the environment because someone was there who had it, who put it into the atmosphere of that environment, and then someone else came in and breathed it. So, you know, there's questions about pathogens in general and infection risk in general. COVID has made us more susceptible and more aware of all of this, but these are general issues that exist. We've known it for some time. The indoor environment has not been perfect. In fact, far from it. Now, ASHRAE, of which I'm a member of, ASHRAE stands for the American Society of Heating, Refrigeration, and Air Conditioning Engineers, about 65,000 members worldwide of professionals, including many people in the national laboratories like Pacific Northwest National Laboratory, who does a lot of work in this area, or the NREL, the Renewable Energy Lab out of the National Renewable Energy Lab out of Colorado, does a lot of work in this area as well. And together, they create these specifications for minimum acceptable criteria for indoor air quality. And I want to bring this to your attention because all the environments you're living in, you're standing in, you're sitting in right now, should conform to these specifications. And in general, they don't. I can tell you they don't because I study a lot of them. I analyze a lot of them. I go and measure a lot of them, and they're woefully inadequate. And that's just evolution. It's history. We haven't had to pay much attention to this topic over time. And now's the opportunity to do it before we have another one of these outbreaks. But I've been in many environments in both healthcare and in buildings, just office buildings, and of course in our homes, where we're nowhere near the minimum acceptable exchange rate and ventilation for indoor air quality. In terms of impact, it has a huge impact. This just shows you some of the impact in terms of cost. We know it costs a lot to have sick people. I mean, these numbers are not going to surprise you, you know, productivity and potential savings. This is 1966 data. You know, we've got 20 to 50% reduction in health-related syndromes. If we clean up the indoor air environment, the potential savings. There's been a book written about this by Joseph Allen and John Macomber out of the Chan School of Business Health in Boston at Harvard. And the book is called Healthy Buildings. And they make the case that if you clean up the indoor air environment and give people a better environment in which to work, that in fact productivity will rise because you'll have less people out sick and they'll feel more healthy. And that will translate into productivity, and it will more than pay for itself. But if you look at it just from a cost point of view, it does cost money to fix these buildings. If you look at it from an economic finance point of view, it's worth it to do it. But we face resistance because many people don't want to do it. Many building owners view it as the last thing on the list. The health of the building is really far down at the bottom, and we're trying to change that. So what you find is that and they've measured this, they have data that measures this, of course, that as the ventilation rate improves, as it goes up, so doesn't the productivity. And this is liters per second per person. So this is the amount of fresh air that's coming into the environment. They've studied this in the classroom. They've studied this in the office environment, that if you have clean, fresh air coming into the environment, you will feel more alert and more awake and have better productivity. I've done studies in California schools. One of the national laboratories, I think it was LBL, did a big study with the schools in California and found cognitive response improved significantly when the kids got fresh air. And they do it by measuring carbon dioxide, which is a proxy for oxygen. The more carbon dioxide there is, the less oxygen there is in a given environment. So they measure it using carbon dioxide sensors, but what they're looking for and what they're really trying to measure indirectly is the amount of oxygen in the environment. So we know this is the case, and we tend to focus our attention on infection control. And this is COVID numbers. But what we've learned is that airborne transmission is the dominant transmission, and that these long-held beliefs about infectious disease transmission are really wrong. Questionable at best is being somewhat gracious, because they're not really questionable. They're wrong. And that everything occurs indoors. There have been no confirmed cases of COVID transmission outdoors during the entire pandemic. And that our heating and cooling systems in our indoor environments play a really important role in risk mitigation for indoor environments. But existing buildings as they are, because they're old and they weren't designed necessarily with this in mind, they don't offer us much protection against airborne transmission. I'm afraid to tell you that is the case. This is an animation sequence. If it works, yeah, it looks like it's going to. I hope this comes through for you. A computational fluid mechanics example of someone sneezing or coughing in this case, and you're watching the plumes come out of their mouth, and those are particles that represent droplets, and you can see when you're in close proximity that it just infects the other person quite dramatically. So hopefully these are not infected particles, these are not virus particles or transmission particles or pathogens, but if they are, you can see very quickly why someone gets infected. So now let me just switch a little bit, and some of this material may get a little thick for you, I don't know, but I'm going to go through it, and if you want me to do it again, or you want me to break any of these down into smaller sections and do them individually, I'm more than happy to do it. My job is education. I try to teach this stuff, so I'd be willing to do it more in the future if you ever wanted me to do it. But let me talk about air change rates. Okay, so it's called air change rates, or ACH, air changes per hour. This is the amount of air that's going through a given environment over the course of an hour. So these are the registers you see in your home or in your office, where you've got air coming out of the ceiling grills and then going through and going back out some other grills. Over here we have supply, and over here we have return, or maybe I did it backwards, doesn't matter. And you want the same amount to go in that goes out, right? It's a loop. And hopefully those are positioned in the right place, and you get this nice exchange. So it really is the measure of volume added to the space over a period of an hour. Or another way to look at it, it's the number of times the air gets replaced in an hour, okay? But they assume perfect mixing. They assume there's no dead spots. So in this little example over here, it's going in and out over here, but over here in the corner, you may have a problem where it's stagnant and you're not getting any refreshed air over there. And so, just because you have 500 going in and 500 going out doesn't mean that it's getting everywhere in the room. That's a mixing problem, what we call a mixing problem. The other thing to note is that this 500 should be fresh air. If you're just recirculating the same air over and over, then it's not much good unless it's going through a filtration system, which we encourage, and it can. But filtration systems require that the filters be changed, and they require that the filter be fine enough so that it catches particles. We have a measure for that. It's called MERV, minimum effective ventilation rate, MERV. And it should be about 13. The MERV 13 is the level that we're looking for. But the location of diffusers makes a big difference too. This is an example of an office environment. You've got supply going in out here and return going on up there. So, this one's far from perfect. The positioning of the supplies and returns is really important and wasn't thought about in the design of your buildings, because your buildings that you're in right now were built before anybody really thought much about this. Most of the time, the location of the diffusers, the air supply diffusers and the return grills, is laid out for cost reasons, not for pathogen mitigation reasons. And we've seen very effectively that in certain cases, and I think this might be an animation sequence, we've seen, this is one of the cases, yes, I'm going to get to play this good. I hope you can see this. This is a restaurant in China that we studied very carefully. I didn't do it. This was done by some scientists out of China who did this work. And you can see that there's these devices up here that are supplying air, and then there's returns underneath. So this is a recirculation device. And you can see these people over here in red. They all got infected. This was a restaurant. This was a very famous case of super spreader event where only people on one side of the restaurant got infected. And they built this animation. They built this is called computational fluid dynamics, where you can actually model this on a computer mathematically. And I'm just going to run it a little bit, and you can see there's the super spreader right there. You can see the super spreader person is emitting the viral load into the environment. And what happens is it gets sucked into this circulating effect here between that heat exchanger, and it gets pulled in, and you see the whole place starting on that side, only on that side, starting to turn red because the air current is picking it up. And you can see the red zone right here. And all the people that you see in red there got sick. And in some cases, they were just facing the wrong direction. They were facing into the flow. In this case, they were near it. So even where you are in a room can make a big difference about being infected. So let me get back out of here. So depending where you are, it can make a big difference. This is another sequence here. This is inside an existing room. This is another animated sequence that doesn't look like it's going to work. Nope. But again, you can see a similar effect just from the image. The air is coming in, people are sitting here, and because of the location of those devices, it can be a situation where you can become very affected. So here's another one. This is another animation. You can see the infected person. And what's happening is the air current over in this region is because there's an air supply right here, it's causing high concentration in this area. So the particles are coming out of the person, going over to this section and accumulating right in this region of the room, causing the concentration to be high over here. Therefore, people over in this section of the room are going to become affected when people over here may not be. So it's not even uniform within a single room. There tends to be zones of safety, if you will, or zones where you don't get infected and others where you get very infected. Okay. So just a couple of animations. This one shows you here what we're looking at is velocity. You see the velocity is not uniform. What happens is it changes as a function of location. Here I've taken a slice down low. This is the same office environment. You can see some dead zones. The dead zone is velocity of 0. And what happens in a dead zone is it typically, and you can see the one over here I was animating before, it typically will accumulate more readily over there. You can see I've moved up one level now. This dead zone is now quite prominent over in this corner, and so on. So what do you do? Well, cleaning and ventilation are really additive. If you can't ventilate properly, it's important to clean with filtration. There's a couple ways to do that. most effective is HEPA filtration. That's the one that you'd really like to have. You can also do it with something called UV, GI, ultraviolet genocidal irradiation. HEPA is high efficiency particulate arrestor filter. So HEPA is as good as you can get. HEPA is what's used in an operating room. An OR, we use HEPAs overhead, and UV is the light. So you can see here that relative risk is number one when there's no ventilation. So you walk into an environment where there's no air at all, and you're going to have a relative risk of 1. And then what happens if you ventilate, you can drop it by almost 40% just by getting ventilation there. Open the doors, open the windows, turn on fans, get some fresh air in. You can do a similar thing with filtration as well. It's not quite as much with just filtration, but it works pretty effectively to have filtration in the room. Again, this is a function of how much filtration, how fast you're moving it, how best it's mixing. You can do both, and in both, when you do them both, it's very effective. A little bit of filtration, portable HEPA, for example, and proper filtration in the HVAC system, and proper air change rate in the environment. So this was empirical evidence that they studied using elementary schools in Georgia. So air cleaners are a way to do that, and ASHRAE recommends HEPA-based filtration as a primary solution. UV is another way to do it. And with respect to 2.5, studies have shown that air cleaners that can handle the 2.5, what's called PM 2.5, there's 2 measures. This actually came from outdoor air monitoring. PM 2.5 are all particles that are smaller than 2.5 microns in diameter. PM 10 are heavier, they're 10 or less. And the EPA has criteria in place for what these numbers ought to look like. And there is a significant statistical association between portable air cleaners in the home, for example, and improved health outcomes. But you need one that delivers enough air. You need one that does in the range of 100 to 300 cubic feet per minute. So you need a good one, I guess is the point. So air cleaners became an important component of this. We got involved with air cleaner development for a period of time, and we built a device that worked extremely well. I'm not going to go into all the detail of it here because it's just one of many that offer. But they work well. They tend to drive particle count down very quickly. This is a plot of how well they work if you have a good one. And you can see that it comes down, from a really high contamination level of 100. What we're finding is that you can eliminate 80% in 20 minutes using these kind of devices. Okay. 60% reduction. Okay, 60% in 20 minutes. 80% in 30 minutes is measured. This was measured. We did a test on the ones we built. NASA did this work and chose it as a device because it performed that well. They were quite surprised. They called us and said, "Are we doing something wrong? It seems to be working awfully well." But that was just how it worked. So anyway, I don't need to go through all of this. What I'd like to do is, I think that, there might be a couple more animation sequences here that are worth watching, if I can get them to run. So this is someone breathing in a conference room without any help. You can see that plume come straight up out of the person. So there's no filtration going on here in this room. And you can see over time that room gets full. This is a typical conference room. The person is breathing normally. There's nothing going on there. They're just having a meeting in a room, but there's no filtration. This is over a 1 hour period in a room without filtration. And you can see there that the room continues to turn red over that period. This is a time step sequence. Again, we're modeling this using computational fluid mechanics, which is the primary tool used to study this without having to get people sick in a room. You model it. And this was a prediction we did using our software. And then, yeah. Mm-hmm. This is an example of the same environment. And if you ran that, you'd see it cleaned up very quickly. So here's, in this case, we put a air cleaner on the table, and you can see the room never changes color because the pathogen's coming out of, and it is running here. You can see it running at the bottom. So this is the same 1 hour period, and the air cleaner's running, sitting in the middle of the table. It turns out it can be anywhere. It doesn't have to be in the middle of the table. You see the room stays blue under the same conditions. So, it makes a difference. Air cleaners can make a big difference. To not necessarily replace what you have, but to supplement it. Hopefully what you have is working. By the way, they should always be on. If you're in an environment on a day-to-day basis and the diffusers overhead are not blowing continuously, it's wrong. They should blow continuously. The way they've been set up historically is they only modulate on temperature. So if the temperature gets high enough, they turn on the air conditioner. If it gets low enough, they turn on heat. Otherwise, they're off. But the off condition is horrible for pathogens because it allows them to accumulate. They should be on fan only. They should be running all the time. And many people simply don't know that. They don't know that. And so they're set wrong. Most of the buildings I enter, they're set wrong. So anyway, this is the point that it's time for a new look at this. There's been a lot of work done on it. It was done during the COVID period. It seems to me that it's gone quiet. Everybody's back to normal and tries not to pay much attention to it. Because I'm talking to people in the healthcare industry, I'm hoping that you'll be more sensitive and use this opportunity as a time where we can build a defense against the next pathogen. They will be more. We know how to fix it. We know how to improve it, but we need willing participants. So anyway, we're beginning now to look at new definitions of health and wellness. There's a push for healthy buildings, and it's air quality, it's thermal health, it's having the right humidity in the room, it's safety, it is water quality. So at ASHRAE we talk about this healthy buildings, and it correlates directly to human health. This is a human health issue. We find that if the building is healthy, the humans are healthy, and they have better outcomes. They have better social outcomes. They have better intellectual outcomes. They have better productivity. These are linked. This shouldn't surprise us. We're 95% of our time is inside of buildings. We need to make them healthy so that the people are healthy. And this is gaining some attention. And I would encourage you to think about it and possibly get us involved if you need it. There has been some great work. This is some work done. I don't know if this is live anymore. This was live for a period of time, but they're able, yes, it still is live. Look at this. So this is some schools in Boston who have started to put air quality monitors into their buildings, and you can read them in real time. So you see here, these are air quality monitors in the schools in the Boston public school system. And it can all be seen dynamically. And I'm just really happy that this link is still working. This is real time. This is showing you the air quality in each of the buildings that Boston has its school system. And you see as you zoom in on it, that it splits because there are two schools there, not one, et cetera. So you can get right down to the individual building and click on one and say, that's the Condon K8 school, and it has a measure of a 64. And they grade them on a scale of 0 to 100 because they're looking at not only a particle count, but they're also looking at oxygen content and other parameters as well. So there's been some great work done. Unfortunately, it took a pandemic to do it. And, we have to overcome barriers, that scientific justification, economic justification, split incentives. You have a multi-tenant building and the landlords live somewhere else and they don't care about what's going on. And that's just a home ownership situation. If you've got a building where you're leasing, many of you in healthcare have been to situations where you actually lease the space from the building owner, but the building owner has different motivations than you do, and theirs is cost and yours is human health, and that's an issue. So we need some better improvements there. It is certainly a barrier that we need to overcome. policy, of course, workforce education, part of what I'm doing today, perception of liability on the part of professionals. I've seen this again. We don't want to know, because if we do know, then we're going to be liable, and then we could be at risk. So these are all things that we encounter. We also encounter resistance at the facility level. Oftentimes facility managers are stressed as it is, they're overworked as it is, people who are trying to keep these buildings alive. And the last thing they want is someone coming along talking about indoor air quality. They're trying to keep the lights on, they're trying to keep the driveway plowed. So I get it, but at the same time, this is really important stuff. And perceived conflict with energy in the environment, that it's not sustainable. It is. You can have energy efficient buildings and clean air at the same time. You just have to work on it and design it to do that. They are not mutually exclusive. Many people think they are, that if you seal up a building, it's going to have bad indoor air quality and good energy efficiency. But we've overcome that with things like energy recovery ventilators, which refresh the air but don't lose the temperature. So they retain the temperature and often humidity while still exchanging the air. So we've been able to solve that through energy recovery ventilators. So, we're afraid that it's going to take liability to fix this. There is more of this going on, where there's legal action being taken because of the poor quality of the buildings and the declining health of those that are in it. I don't know how far that's gotten. This was, of course, 2022 when this was done. But the point is here, and we've been stuck here for quite some time with inadequate or mediocre indoor air quality. And the pandemic created a strong motive for us to redefine these goals and address it in a real good way. It's not a technology issue. We have the technology. The outcomes are great. There is a growing understanding, but my feeling most recently is that everybody wants to forget about the pandemic. Nobody wants to think about it anymore. So I'm having a little trouble keeping the attention focused on indoor air quality. Now, choices you make can be important. I used to teach this a lot when I was talking about pandemic and COVID itself specifically. Whenever you enter an environment, particularly a room, and I think here about a pub or a bar or anywhere, particularly where there's low ceilings, watch for low ceilings. Low ceilings mean the volume is low or small, and the concentration will be higher. So I always think about people, place, time, and space. How many people are in the room is sort of the first one. How large is the room? Are there any air cleaners there? Is there any air moving? Can you feel air moving? If you can't feel air moving, it's not a good thing. Time, how long are you there? Remember, it is a function of time, because the longer you stay, the higher the probability that you will catch something. And then how much space is there between people? It is still important. As you saw from that animation sequence, distance makes a difference between people. And so you want to keep your distance. So that's what I had to say today. I don't know what time it is, 4:49. That's not too bad. I'd certainly be open for any questions, Emily, if there's still anyone around.
Absolutely. Yeah. Thank you so much, Paul. That was extremely, extremely interesting. And we have a few questions in the chat. So thank you for leaving some time to address those. I'll ask folks to unmute if they're able to, and you can ask the question yourself. Caitlin, are you able to unmute?
I am. So I was curious. I apologize for the wind in the background. I am that person who always tries to be outside.
Good.
Um, so I was curious when you were talking about the impact of humidity on particulate matter. Does that rule apply as well to kind of interstate air pollution concentrations and how you see those shift with air currents?
Yes, it's not unique to the indoor environment. Humidity plays a big role in health, independent of indoor or outdoor. The difference is that concentration of pathogen will be much lower outdoors. So it's not a pathogen issue. It's still a respiratory issue. If humidity is low, your upper respiratory tract will dry out, and it's not as strong as a defender if it's dry. So this is why people get sick in the winter. It's not because of touch. It's because our cilia dry out, And the cilia in the upper respiratory tract is a key defense mechanism and prevents these little particles from getting in deep into our lung tissue.
Thank you.
Mhm.
Yeah, thanks, Caitlin. Joanne.
Yeah, thanks very much for a really informative presentation, Paul. So 2 quick questions. When the air filter was on the table, then you said, well, it could go anywhere. And then I'm like, well, wait a minute, what about that airflow thing? Like, I have visions of my dining room table probably being covered with germs and underneath not so much. So, but
Yeah.
you're saying the air filter could go anywhere, right?
Yeah. So here's the thing. The
Yeah.
big difference is whether there's one or not. Okay. So if there's
Okay.
one present, then it makes all the difference in the world. That's a big step function. Beyond that, we find a secondary effect about placement. Centralization is best. That's why we stuck it on the
Okay.
table in the center. But I've put them on the shelf before and it works well too, because there's so much air coming out of it that it drives
Right.
mixing. It drives down the concentration. Remember as well, it's sucking into the filter all the bad stuff.
Right.
So it's really quite effective, as we found out. We first thought placement was going to be more important than it was. And what we found out through both modeling and testing is that it doesn't matter. In fact, in the case of NASA, well, you know what they did? They put it on the floor next to the inlet grill because that's where the air used to come from. So they put it on the floor because they wanted to model the worst case condition. They said, well, let's make a worst case condition. And they saw the same outcome. They saw the 80% eliminated in 30 minutes, and they went, whoa, whoa. And they called us up and said, look, what have we done wrong? Our data looks too good. And we said, no, that's what the data does. That's what it does. Yeah.
That's a good question. And then it was interesting to see the school buildings numbers. Which way are you looking? Like, are the numbers, the lower the number, the better, the higher the number, the better?
I think it's 100% is good. And so they were
Okay,
running in the high
thanks.
90s. Yeah, I think that's an
Got it.
IA2 number. And so they try to get it to be 0 to 100. And not my favorite number because it's an aggregate, if you know what I mean. I tend to look at
Right.
CO2 count directly and PM2.5 count directly, but that's because I know what to look for, and not everybody
Right.
does. So they try to aggregate it and come up with a number of 0 to 100, where 100 is good.
Great. Thanks so much.
You're welcome.
Thank you, Joanne. Paul.
Mhm.
Hi, Paul, yeah, thank you for the wonderful presentation. It's just so fascinating and so important. So let's hear it for outdoor dining. How hopefully that will stay.
That's here for outdoor dining. Yes, I like
Yeah.
outdoor dining. Yes.
Yeah, excellent. So it seems like the biggest bang for the buck, as it were, is for the public spaces, the larger buildings, the schools, the churches, the workplaces, the conference rooms, the convention halls, bring a lot of people in. It's going to be a big challenge for residential buildings to get significant ventilation and filtration, but it's not so important if you're just with your small family. But certainly there should be a lot of pressure on public buildings to come up to these standards. How close are we to getting these standards for our public buildings?
There's a push going on right now by the White House. I've never seen anything like it. There's a push going on by the federal government that they've seen this as both an opportunity to make change and also a public health issue. So there's a push, but I'll tell you that it's not in any of the codes. It's not in any of the building codes. So there is no requirement yet to ensure that we have proper indoor air quality. And it's part of the reason I'm trying to educate you all, because it's up to us right now to demand it, to ask the question, hey, what's going on here? Has anybody looked at this? Is there an air change rate? Do we know what it is? Particularly in healthcare. And I've told you that I've looked in healthcare, and it's not a pretty set of outcomes. That we unfortunately are still suffering from antiquated systems, aging systems. Many of the pieces of equipment I look at date back to early 2000, in terms of initial placement. The design that was originally specified is inadequate compared to what's required today. And the level of filtration is too low. They go for price. They go for MERV 8 filters, which are cheap, instead of MERV 13, which which trap more particles. And they'll tell you, well, if I go to a MER 13, it's got more resistance and it's going to be hard on my motor and my motor will burn out. And so I can't do it. So I get a lot of excuses, Paul. I really do, that it's too expensive. Like I said, the barriers, it's too expensive, can't be done, isn't worth the investment. I don't believe the science. So it, like climate change, is something that we have to continue to work on. They aren't completely dissimilar in that regard.
So even with a new hospital being built, there aren't the requirements or standards. It's all voluntary to meet these higher
Depends
standards.
where you are. It depends where you
Okay.
are. And it's state by state, Paul. So it's not, for example, in the state of New Hampshire, there is no requirement and there's no minimal standard. And by the way, there's no required commissioning. So there's no commissioning required in the state of New Hampshire. I've testified on this several times at the legislature. I was there again this year. No commissioning required. So commissioning is the idea of testing the building to make sure it meets the specifications set that by, in this case, ASHRAE or anyone. Energy is the same way. You can have a building built in New Hampshire, residential or commercial, and have it not meet the minimum codes, and no one will know it because there's no testing being done. That's where we are today in New Hampshire. It's not that way everywhere, but that's what I got in New Hampshire, I'm afraid.
So
And that's new buildings. You asked me about new buildings. Existing
Yeah.
buildings are nowhere near it. No one ever tests them. It's ironic. I find it ironic that we have our automobiles tested every year for safety, but we only spend 15 or 20% of the time in our automobiles. We spend 95% of our time inside buildings, and those have never been tested and are not required to be tested periodically. Go figure.
I'm sorry, I have two more questions.
Sure.
They kind of go hand in hand. So what practical things would you want us as healthcare workers to really emphasize when we're recommending to homeowners about central air conditioning and heating? And then to piggyback off of that, are you aware of any financial incentives that they could apply to, or trying to think of I'm drawing a blank on the word, but essentially rebates to help people afford it?
Unfortunately, no. On the rebate part, they did have some for a period of time, but I'm not aware of any at the moment. The state had a program through the state office that was using COVID funds to help offset the cost of some of these improvements, but I don't think it's active anymore. And with respect to making people aware, I think it's most important to make them aware that ventilation is really important, and or filtration. If in a home or work environment you can't get one, you should at least get the other, and preferably both. So I've had people who have told me it's been a life-changing experience to put a HEPA filter in their environment. And that's primarily because the HEPA filter is taking the particulate out, and the particulate is aggravating them from an allergy point of view, or they're continuing to get sick. I wish I could put one in every daycare center, I'll tell you, because daycare centers need them. And I've been to daycare centers, but again, it's an economic issue, and they're trying to economically hold on to the situation, and I'm asking them to buy filters. So it's tough. Education, I think, and awareness are the big things.
This was incredibly helpful and informative. Thank you.
You're welcome. My pleasure.
Yeah, thank you so much, Paul. And I look forward to being able to share with the rest of the group. As you just said, education is so important. So thank you very much for giving us your time tonight and speaking to our group. And I look forward to continuing to learn about indoor air quality as we learn about outdoor air quality with climate change. And I want to thank everyone for attending as well. So have a great rest of your night, and I will follow up with the recording link tomorrow.
Thank
All
you.
right.
Thanks so much. Thank you.
Bye now.
You.